Welcome to a presentation about our publication for emnlp 2022. Our publication is about an extensive survey where we trained different machine learning models on common NLP tasks and then looked at how do they react to differential privacy. But first of all, we're going to talk about why do we need differential privacy, then what it actually is, and how can we implement it in terms of deep learning and PyTorch. Then we look about our experimental setup, the hyperparameter tunings we did, and the results, as well as the conclusion, goal, and future work. So in today's data-driven society, data from us is gathered almost every single day. And oftentimes it is done without us even knowing about it. So it's very likely that each one of us is part of a data set that was used for a company to train a classifier on. Then this classifier is then used to offer a service for us. So one could simply say, okay, why should I care about privacy if this data never leaves the company? And it turns out that machine learning models have the tendency to actually store data or store insights about the data set that was used to train the classifier. So if a company decides to make a classifier public, then people could gain insights about the training data and therefore gain insights about you. And one can then say, okay, so this is called a privacy attack against the model. But one could simply say, okay, why should I care if I use like a handwritten digit classification? But let's think about more sensitive data. And especially in a P realm, we have medical forms, financial forms, political statements. And for example, for political statements, one could simply argue saying, okay, but it's made public if you look at like a Twitter data set. But that's true, but deep learning models give us the opportunity to do an extensive analysis with a lot of people very, very quickly. This is not possible when doing it manually. And additionally, we have a dilemma, because on the one side, we have the researcher that tries to do good with the data, but then on the other hand, we have the data holder that we need to protect. And especially in sensitive areas, there is a greater hesitance to use natural language processing as a tool for analysis for sensitive areas. And those research questions, those sensitive research questions, tend to have a greater impact on doing good for human society. And oftentimes, we can't even do the analysis because privacy laws prohibit us access to it. Now, there are different privacy attempts that try to say, okay, we need access to that data set, so let's, for example, anonymize the data. So saying we eliminate all the data samples that give us hints about who is the data holder about that data sample. And actually, this is not enough, because it has been shown that we can de-anonymize the data set by using other data sets additionally. The other option would be, okay, let's train our models remotely. Saying, for example, if you want to train a cancer classifier, we send our code to the hospital, and then on their servers where the data is located, we simply train the classifier, and they then send us back the classifier. But as I already mentioned, those classifiers have the tendency to store insights about the data. So those two attempts are not sufficient to protect the data holder. We need something else. And what we need is differential privacy. And before I go into the mathematics of differential privacy, I first want to talk about the intuition. So let's imagine we have two data sets, D1 and D2, and those are identical. And each of these rows is an individual. Now D2 has one individual missing. That's the only difference about D1 and D2. Now we perform a function against that data set, F. That could be a sum function or a neural network. And what we're interested in is the maximum difference of that function, meaning if we eliminate one row, that contributes to the maximum difference of that function. And this is called the sensitivity. And in differential privacy, we want to kind of bound that sensitivity, because the sensitivity gives us insights about the training data set. For example, imagine if this is a cancer data set, having 1 as the patient has cancer and 0 the patient does not have cancer, we can simply run a sum function on this one data set here and that data set here. And if it stays the same, the person does not have cancer. If it's different, then we know, okay, that person had cancer. So without even looking at this one sample, with simply looking at the difference, we now gained an insight about a single individual. So now let's look at the formal definition of differential privacy. So if we have a randomized algorithm M, and this could be the neural network or the function we run against the data set, with the input domain of the data set, then we call it epsilon delta differential private if for all outputs of that function or the random algorithm, and two inputs, x and y, where those are two data sets with one row missing, the same sample we just had, then we say this difference is bounded by e to the power of epsilon. So epsilon bounds the sensitivity, the maximum sensitivity, plus delta, and the delta is just the probability that the boundness with epsilon breaks. So let's say we have almost all the time a boundness expressed by e to the power of epsilon, but then if the function is just right and the input data is just right, this kind of boundness breaks, but it's very, very slim. So this is very, very, very small, the delta. For example, in our examples, we use 10 to the power of -5. Okay, then let's look about how can we use differential privacy for neural networks, because this is just a mathematical expression. And before we go into how we use it, I would first want to talk about stochastic gradient descent, usually with nothing different. So we have the input data, and then we have our neural network. We then run it through the forward pass and get our predictions, and together with our true labels, we get a loss function, get the gradient, and do the backpropagation and updating of the parameters. So nothing strange here. So with differential privacy, all the steps until getting the gradient stay the same. Now, that means that we can use any method to obtain the gradient. But once we got the gradient, we clip it. And we clip it because we want to bound that sensitivity, meaning we want to save also all the outliers. And imagine if you have an outlier in a data set, you also want to protect that individual, meaning you have to use a lot of differential privacy and screwing up all the other data points that are where it's not necessary to do as much of differential privacy that you need for that one outlier. Once we clip the gradient, we then add noise. And this is what makes the algorithm differential private. And that noise could be Gaussian or Laplacian, there are different methods. Now, once we have that noise, have the noisy gradient, then we use that to update the parameters of the model. So this is what we did, and we did that for different tasks, for sentiment analysis, natural language inference, entity recognition, POS-Tagging, and question answering. Let's quickly talk about the data sets. So we used IMDb for sentiment analysis, SNLI for natural language inference, Connell 2003 for named entity recognition, Wikian as well. And then also 2 data sets for POS-Tagging and Squad 2.0 for question answering. For our models, we used the BERT-based model, where we had 2 different settings. The first one was we had a linear layer at the very end of the BERT model, and then also one where we had a bidirectional LSTM in front of the linear layer. Additionally, without the LSTM, the models without the LSTM, we trained them with fine-tuning the last 2 layers and fine-tuning all layers. Then as well, we had the extreme distal transformer model, where we had very similar settings to the BERT model. Our learning rates were in that range, and we used the optimal learning rate in our results, of course. And for differential private setting, we first trained the classifier with an epsilon of 1 with all those different learning rates, and then chose the optimal learning rate for all other epsilons. Talking about epsilons, we use epsilon 1, 2, and 5, and 10 to the power of -5 for our delta. The batch size usually was 32, and when once it didn't fit on the GPU, especially with differential privacy, we decreased it by the power of 2. And we did all of our experiments that can be seen in our paper with 5 different seeds. So now we know what differential privacy is, why we need it, and what different tasks we have. Now the question is, how can we actually implement it with PyTorch? And for that we used Opacus, and how that works is as follows. So we have our model, and then we have our optimizer. And once we obtain the gradient, we use the optimizer then for the model. With differential privacy and Opacus, there's an additional concept, which is called the privacy engine. And in that privacy engine, we declare all the privacy parameters, for example, epsilon, delta, and so on. We then take the optimizer and attach it to the privacy engine. So once the optimizer obtained once you obtain the gradient and want to update the parameters, the privacy engine can add the noise and then give it back, and the model can be updated. And how it's roughly done in code is as follows, where we have our model, our optimizer, and then our privacy engine where we attach it. Just a quick side note before we jump into the results. In general, we are interested in an epsilon of 1 for differential privacy because this is considered good privacy as it corresponds to the randomized response. But we additionally did an epsilon of 5 just for analysis to see how do the models react when being introduced to different kind of amounts of differential privacy. So this is the result for sentiment analysis. And first we can see that all non-differential private models achieve very good results. And additionally, all the F1 scores for all those models decrease as well, which is also expected. However, fine-tuning all layers for the BERT model results in an unusable model, which is very odd. And it actually predicts simply negative, as you will see in a second. And the best model for the BERT is the transformer with the last two layers fine-tuned, and for XDTM is the all layers fine-tuned. So this is the confusion matrix for sentiment analysis BERT where all layers are fine-tuned. And here you can simply say it doesn't matter if it's negative or positive, the model simply predicts negative. Next, let's look at the results of NLI. And here first we see for the BERT model that the BERT model where the last two layers are fine-tuned has a huge decline in accuracy. And this is very contrary to the XDTM where that results kind of stays the same. The best model for BERT is a fully fine-tuned one, and for XDTM as well. Let's have a closer look into why does the BERT model where the last two layers are fine-tuned actually decreases in accuracy. And if you look at the confusion matrix for the BERT model with the last two layers fine-tuned, we see that it has problems predicting neutral statements and says most of the times they're contradicting or entailed. Now for named entity recognition, we see that those two models hardly have any drop in accuracy. And keep in mind the scale here, because it does look like they have a larger drop, but it is very, very little. And additionally, XDTM kind of fails learning their task because even the non-private models are not very good. Now the question is, what is the difference between this task where the model fails to learn it and all the other tasks we saw before where the model has had a very good accuracy? And if you look at the data set, and we see that, for example, the O tag here is very much represented or overrepresented, while this tag here, for example, is underrepresented. And if you look at the data set beforehand, we see a very evenly distributed data set. So we can say that these data sets for NER are actually skewed. And if you look at the per class accuracy, we see that overrepresented classes have a higher accuracy, while underrepresented classes do not. And taking even a closer look into the two confusion matrices, on the left hand side we have the non-private one, and on the right hand side the private one, we can see that the non-private model often confuses the position of the tag, meaning the I or the B tag. But the private model also confuses the tag itself, the type. Now if you look at Wikian, we see a difference in accuracy, because those models here are actually very good. And one possibility why that is could be because the tag size is reduced for Wikian in terms of kernel. Now for POS-Tagging, we see that the best model is the transformer model that was not fine-tuned for BERT. But for XDTM, again, the all layers fine-tuned one. So we can see, again, no similar pattern here. And the other data set, GUM, that we also trained on POS-Tagging, we see similar results. And now again, just a quick side note, also like the NER, we have overrepresented classes like so, the noun or the verb. They are also favored by the model. Now finally, for question answering, we actually have different results for the BERT model and the XDTM. For the BERT model, while we have a rather good model for the fully fine-tuned one, all models jump to 0.5 F1 score once it's being introduced to differential privacy. And if you look at the predictions, we actually can see that they simply predict not answerable. Because the data set consists of 50% not answerable and 50% answerable, and so it also is a skewed data set. For the XDTM, we kind of see similar results for the fully fine-tuned one, but for the other models, they actually sometimes predict spans, and those spans are not incorrect, that's why they have a little less accuracy. Now let's conclude with the cross-task analysis. And this is for the BERT model. And for the BERT model, we can't really see a clear pattern, meaning while not being introduced to differential privacy, models tend to say, if it's a bigger model and more fine-tuned on a specific task, we achieve higher accuracy. This is not the case for differential privacy. Differential privacy is highly task-specific, as we have seen models being better in one task, but being the worst in the other task. However, if you look at the cross-task analysis for the XDTM, we can say that for all tasks except NER kernel, the best model was the fully fine-tuned one. Meaning, if we compare this to the cross-task analysis for BERT, where we had no clear winner, we can say that not only if we look at one model, different kind of fine-tunings impact differently depending on the task, but also the model itself is highly task-dependent. Now, the goal of this work is to guide future researchers and motivate the usage of differential privacy for analysis with sensitive data. And we also wanted to address the scholarly gap in literature, and because since to this date, this is the first survey done on several NLP tasks with differential privacy. So we wanted to shed light on the behavior of neural networks in NLP and evaluate the effectiveness of different models implemented with differential privacy. And to motivate it, we also have to talk about the downsides of differential privacy. So the researcher has to assess the sensibility of the data, meaning we have to leverage the accuracy-privacy trade-off. For example, if we have very sensitive data, and it's okay for a model to be a little bit imprecise, then we definitely should use differential privacy. However, if we have not as sensitive data, and it's very crucial for a model to be highly accurate, because if it's a false prediction, it has negative impact, then we should omit differential privacy. And additional to the accuracy-privacy trade-off, there are also higher memory consumptions when training the model and longer runtimes. And talking about the training times, we have a table here that says on the one side the epoch time without differential privacy, and on the other side the epoch time with differential privacy. And here's the difference displayed. And we can see that we always have an incline in the epoch time when using differential privacy. And especially NLI and question answering have a huge difference. And the reason why that could be is because those are very large data sets. Now, just for completion, the difference between the BERT and the XDTM, we see that the XDTM has a lot less training time than the BERT model. Again, here's the difference without and with differential privacy for the two models. It can be seen here. So to conclude, one size does not fit all, meaning there is no best model over all tasks that can be used with differential privacy. The best model is highly task specific. Then also, skewed class distributions are more problematic with differential privacy, as the models tend to overfit on the overrepresented classes. Therefore, we need to use an appropriate score to take into account the class distributions, or the Markov F1 score. And then finally, it is necessary that we have to account for higher memory consumptions and runtimes. And about the memory consumptions, very often we had to reduce our batch size because with differential privacy, the batch didn't fit on the GPU. For future work, we would suggest looking into different architectures of BERT or completely new architectures, as we have seen that even between BERT and XDTM, we have a different behavior. Then also, while doing that, more clearly looking into how fine-tuning affects differential privacy and why that is. And then finally, we haven't looked into generation tasks yet. Those are my sources of this presentation. And again, thank you very much. If you have any further questions, you can look at our publication that we can find on the right here, or email us.